record on this. Yeah, so you don't have control over the thing. So a TensorFlow is both high level and low level. So you can do easy things, but you can customize them as well. With Keras, you can't customize. It's very high level. But with Pytorch, you can do very complex things. So Keras is the most easiest thing. You want the most easiest thing, you go with Keras. A little bit difficult, harder. You have to understand what's happening inside. And I think if you are working with machine learning, you should know all of them, but you should know the maths and each step, why this step was done, why this step was done. So those type of things. So TensorFlow can be done for fast and large data set. It has this as well. So the easier it is, the more popular it is. So popular, a little bit less popular, and worse popular. And yeah. So a lot of what you said was correct. All of it was correct. Like these tools are high level. This is low level. So we will first see. So what is a tensor? Can anybody say what is a tensor? Yeah.
It's like a higher dimensional matrix. Like once you get beyond 2 dimensions, 3 dimensions, they're all sort of tensors. Once you get multi-dimensional vectors.
Nice. Okay. So if it's zoom in. What's happening? Okay, zoom in. Nice. If we used NumPy, what would you call this? An array or a vector, which is a one-dimensional array, you call a vector. Okay. And what is a scalar? Like in terms of machine learning, what is a scalar? So if you're doing machine learning, a scalar is 0-dimensional. So let's say u equal 6.23. So I would say u is a scalar because it has 0 dimensions. It's just a value. So scalar is a value. And if we are doing Python, a one-dimensional collection of scalar is a vector. And it's the same thing for tensors, but you can have multi-dimensional. You have multi-dimensional arrays, right? Tensor is basically an array. So a collection of scalar values. Okay. And it's same as a NumPy array. You can even convert a tensor to a NumPy array and a NumPy array to a tensor. If now, how do you install Pytorch? Okay, that's an important question. So you had a question. I forgot your name. Sorry, Jacob. So Jacob had a. I forgot all of your name, but I will. I'm trying. You have to be. Yeah. So this video, I found like I have done a lot of course, like a lot of tutorials before. I was interested in machine learning and I did a lot of tutorials, but this PyTorch tutorial is very like easy to understand, and it also gives you the like gives you the underlying maths behind all of it. So I would send it to the 586 channel, add channel, browse channel, 586, join channel, and then, so this is really good. And this actually shows you, okay, so you have this, wait, I need to get it 180p. So you select which Python you have, which you want a conda package, and it basically shows you what you need. Also, you need, if you want to run it on your device, you need a NVIDIA graphics card, okay? But you can run in Google Colab as well. Then you don't need anything. You don't even need to install because Google Colab already has it. So here it's very descriptive and it tells you that, okay, the latest CUDA, you have the latest CUDA, but you cannot but if you go back, you see it's not supported. 10.1 is supported, right? Then it shows you that you have to install a legacy version of the CUDA legacy releases, and then you can it also shows you how you go to the terminal or Anaconda prompt and you create a virtual environment, because you know these type of thing break and you want multiple, like you might see nothing is working. So it might be you need to create a new virtual environment and install all the libraries. Okay, so it creates it and it installs everything you need. Okay, so you can follow this tutorial to do it if you have a NVIDIA graphics card. If you don't have an NVIDIA graphics card, you can do it in Google Colab. So for Google Colab, you see, you can go to runtime and you change current runtime type to enable the GPU. Okay. Does anybody know about CUDA? What CUDA is? You are lucky that I did a CUDA programming course in UBCO. It was fun. So basically, CPUs, they can handle intensive work, but GPUs has a lot of threads, but they can handle lightweight works, but they have lot of threads. It's like, you know, you have, so the professor Scott Fraser Lee, who taught it, do you need 2 bulls or 1,000 chicken? Who will win the fight? But if it's like a task that the 1,000, like if you tell 2 bulls to pick up seeds, but if you have 1,000 chicken, it will be better, right? So think of that analogy when you are doing CUDA programming. Basically, CUDA programming is computation with your graphics card. And it leverages that you have lots of threads, but low power threads. They can do low power things. Okay, so you enable, by default it's CPU, you enable GPU, and when you first run this, you have to import Torch. You don't have to install it in Google Colab because it's already installed, but you have to import import it. Yeah, import it. And then if you run this, torch.cuda is available. It will show false, but when you enable the GPU in runtime, then it will show it true. Okay. And you remember NumPy, you have NumPy.1s, NumPy.0s, NumPy.empty. You have all of those things for Torch as well. You can define NumPy like torch shapes. You can even go like multi-dimensional, like 4, 5. So this is 4 dimensionals, but you know, it's basically NumPy arrays. So it has, so if you think of it, it has 5 columns of 4 rows, and there are 2 instances of this and 3 instances of this. You get the idea. Like, you don't have to, it's just arrays. Forget about dimensions, just arrays. Okay. And this was 3x2. Empty generates uninitialized values. So it's you can generate ones, you can generate zeros. By default, the value generated is a float 32 value, the data type. But you can change the data type if you add in another parameter that you want it to be an integer, then it's an integer. You know what float is, right? Float are values with decimal points. Okay. So you can do the same thing you did with a NumPy array, which is you can multiply, add, divide, everything. Same. Forget about Torch. It's basically a NumPy array. And so similar commands, right? You had np.rand, you have torch.rand. So that was one of the integrated with Python language. See, so you know Python, you know Torch. Okay. I was here. Lost. So next is you can even use reshape. And can anyone? I told you this before, but anyone can say what's the -1 for? -1. I told you this before. Yes. Yes. So here I have 4x4 4x4 shape, right? It's a 4x4 array. It's a 2D array with 4x4 size, right? And when you are reshaping, you are telling, I want 8 rows, and I'm too lazy to calculate what will be the column number. You calculate for yourself. Just give me 8 rows, reshape it. So that is what the -1 is for. Okay. I'm lazy. I don't want to calculate the shape. I know I want 8 rows. You calculate what's the column number. So yeah, basic simple things. Now let's get into Pytorch specific things. So you first have to check if the GPU is available or not. When you have the GPU, one more thing, I was telling you CPU and GPU, right? CPU has low memory, GPU has big memory, but the data stored in CPU cannot be calculated. Like you cannot add two numbers in GPU if it's stored in the CPU. So what you have to do is manually, okay, put this into GPU and then add the numbers. And then you want to print it, you want to do something with the number? No, you can't. You have to bring it back to the CPU and then here's the number, okay? So that's what they did. There are two ways of doing it. Here you can see I directly initialized the value, the array in the GPU. Okay. And what else I can do? I can make it in the CPU. So when you do this, it's in the CPU, and then I move it to the GPU. So two ways of doing it. You can follow whatever way you want, and then I can add them and store them in a variable. But here, when I try to do something with it, you can print it. But if you try to do something with it, like convert it to a NumPy array, it will throw you an error, say the thing is in the GPU, you have to move it to the CPU first, then you can use it. So then you can just move it to the CPU and then do what you want. Is that clear? Yeah. So when you are doing Pytorch, you will be using this, and that this is also in the playlist that I shared. Like I'm just going over because I feel it's really good. So I would advise you to go over the playlist, but these are the high level things I got from that playlist. I learned it from other places as well. It wasn't as comprehensive as this playlist, so I recommend that. So another thing is, if you know you have to do, we have to optimize things, right? To optimize things, you have to find the gradient. And and so you have to, you want to optimize something, you have to tell PyTorch, okay, this is what I'm going to optimize. So please take note of its gradient every step. Like whenever I use this, please also compute the gradient as well. So you need to give this command if you want to optimize a certain value. So we will look at an example. I'm just showing you the high level things. Okay. So here I told it to keep the local gradient of that array. Whenever I use it, always calculate the local gradient. So see, I have added 2 with it. It calculated the gradient. And if I do more calculations with it, it will also calculate the gradient. And finally, it always whatever you do with that value, it keeps on calculating the gradient, because I used x here, and then because y is a part of x, it keeps on calculating the gradient. Okay. I will need that for forward and backward propagation later. So, and you can print it. Okay. Now, but did the professor go over forward and backward propagation? Not yet. Okay. Does anyone know about forward and backward propagation in neural networks? You have some of you have some idea about it. Okay. So what happens is you have to iteratively reduce the loss. Okay. How you do that is you update the weight. But after every iteration, you have to make the gradient zero. Like you have to again start calculating the from scratch. Like so, in every iteration, at the end of the iteration, you have to, because what do we want to optimize? The weight, right? So after every iteration, you have to tell Pytorch, please like make the gradient zero. You have to make the gradient zero. And when you are updating the weight, when you are doing the backward propagation, you are basically updating the weights. So that has to be done with where you don't track the gradient. Just for one instance, when you update the weight. So there are 3 ways of doing it, but this is the like best way. When you are updating the weight, you put it inside this function so that Pytorch doesn't calculate the gradient for that. You know, just for one, it will always calculate the gradient for weight because weight is what we want to optimize, but don't calculate it when we are updating the weight. That's one thing. And when we are done updating the weight, we set the gradient to 0, the weight gradient to 0. We again have to calculate the gradient from the start. So 2 things. When we update the weight, we don't want to calculate the gradient. And when we go for the next calculation, we want to set the gradient calculation to 0. We want to again start calculating the gradients again because it's a new, it's like initializing from the start. Yeah. So so yeah, it's just we want to optimize weights. We can use an optimizer. After each step, we have to set the gradient to 0. This code doesn't run, it's just an idea. Okay. Finally, so you need some theory. You will get no more theory in class, but just to make you understand what's happening, there's some theory I need to show you. Okay. We did differentiation in high school, but you don't need to understand that much. Just that this is our result. let's say you have you have your input, you have your weights, okay? And multiplying your input with your weights in a function, you get your output, which is the prediction. Now you have a prediction and you have a target, right? You already, in machine learning, you already know what is the actual result, and this is the predicted result, okay? Z is the predicted result. So what is loss? Loss can be actual result minus Z. It's a simple loss, okay? Actual result minus the predicted result is your loss. So the gradient that we have to find is our, because we want to optimize the weight so that the loss becomes lower. So we have to find loss in respect to our inputs. So loss, let me just double check. Okay, loss with respect to the weight, because we want to optimize the weight and we want to reduce the loss, we have to find the loss with respect to, let's say X is our weight, because we want to optimize our weight, right? So, you know the chain rule? Chain rule is nothing. It basically says that if you want to find, make it bigger. Okay, if you want to find d loss by dx, you can do it by d loss of z and dz of dx. Like the basically, when you do this, when you, because you know the function, you can find dz of dx, because you know what the function is. You can differentiate it and you can get this. And because you know the function here, what's our function? Actual minus predicted, an easy function. So you can find the loss with respect to this. The z is the function. So, and then you can find the final result by the local gradients. So the final gradient will be local gradient multiplied by local gradient. Multiplication of all the local gradient will result in the final gradient. If I can, like, I'm giving you an overview. Like, this is, the math goes deeper, but it is, this is what it is. And let's check out. Oh, and the forward propagation. This is the forward propagation, that you are getting a weight and the input and getting a value, right? Getting the prediction is the forward propagation. And what is the backward propagation? Backward propagation is updating the weight. Updating the weight is the backward propagation. What do we, why we do forward and backward propagation? We want to minimize the loss, okay? So we do it until we minimize the loss, and it will just take 1 minute to end my lecture. Is so this is important. We have a X, we have a Y, okay? X is our input, Y is our final output. We are initializing the weight to 0, okay? We have input, output, and weight. So we multiply our input X with the weight to predict the Y. So forward propagation is the prediction. Simple. Our weight multiplied by our input. Done. What is the loss? So you know, this is I told you the prediction minus the actual value is the loss. This is, we use mean squared error, but this is just mean squared. We are not, this is mean squared. Yeah, mean squared, like mean squared error. So just getting the difference between the prediction and the actual value, and we are squaring it, and we are finding the mean, like 1 divided by n. So this is a standard loss function. We have a learning rate. What is learning rate? So the intensity with which you update the weights. If you have a high learning rate, you might not converge because it will be like jumping always. You are, so you need, if you have a really low learning rate, it might never converge. You need a balanced learning rate. And this is how many times I run the loop. So basically what I do the forward propagation, which is predict. I have a loss, right? So I calculate the loss of our prediction because I know what is the actual value, and find gradients. So that is basically, I find this d loss divided by weight because I want to optimize weights. And you can see the only thing I want to track is the weights because I want to optimize the weights. Okay, requires true. Like, and finally, I did the weights are updated based on the learning rate. And so this is basically W equal to the new weight will be this. You know the gradient, you know the learning rate, you change the weight so that it reduces the loss. And we do it inside, because remember I told you we don't want to track W when we are updating the weight. So we do it in a, don't track, just I am not tracking this, okay? And we don't set the weight to 0. Remember, we set the gradient that we calculated to 0. We want to start from scratch again. We did one calculation. We use that gradient to update the, we use W dot gradient to update the weight, and then we initialize the gradient again. And we do it multiple times, and see, it had a big loss, started from 30, and slowly we are converging. And the weight, the weight is getting changed. So I'm very proud of myself that I could do that. Yeah, but this is basically how you can use it. And I would suggest you to go through the tutorial. Yeah. Nice.